Hello, welcome. My name is Craig Otto. This is a advanced tools example, basically focusing in on process capability. And before we get into that, I just want to do a couple of sort of reminders. The basics of process capability are all based around normal distribution, and there's some assumptions with that. A normal curve is bell-shaped with the highest point at its mean. It's symmetrical about the mean. Basically, each side is symmetrical of itself. The curve, as you can see, as it gets out here, it approaches the horizontal axis, but it never touches or crosses it. And then, your transitioning points between the convex and concave here is basically plus or minus 1 sigma on both sides. And basically, I just wanted to refresh that. And with that, there's rules and statistical backing of it, where plus or minus 3 sigma, you got 99.73% of your data that falls between that. That becomes significant when you start talking about data from processes. For example, if you're monitoring a process, you can use what's called statistical process control, and it'll trigger you when something happens that's not probable, much like this example here. So basically, before you do anything in terms of assessing capability, you need to make sure, number one, that the process follows a normal curve, and number two, it's within control, within the guidelines of statistical process control. And if you're not familiar with that's another day review of or examples. So I'm not going to get into the rules of SPC and normality right now, because I want to get revolving around capability, but it's important to understand that as well. So what is capability? Basically, when you look at capability, you're comparing the process spread of your process plus or minus 3 standard deviations to a specification limit. And that could be set by a customer, internally, whatever it may be. But you're trying to determine, is a machine or process capable of producing things within specification. And to do that, we have 4 basically capabilities that most people use. One is CP, one is PP, one is CPK, and the other is PPK. I'm going to go through an example to demonstrate each one of these different measures. Okay, and I'm going to go ahead and I have an example here of data. Basically, you have different tools on different days. You have a front, mid, and rear. You can take the average of those in a range of those different measurements. And what we want to do is assess its capability. And one of the things that you want to do first is assess the CP. Now the CP, if you look down here in our little chart or table, basically shows it's the upper spec limit minus the lower spec limit divided by your 6 standard deviations. And you may also notice that the PP, process performance index, upper spec limit minus lower spec limit divided by 6 standard deviations. It's the same formula. The only difference is, and they don't show it on here, but there's a different type of standard deviation used, and that's the difference between the 2 different formulas, and I'll go through that. Okay, so the only difference between the CP, the CPK, compared to the PP and PPK is the standard deviation used. So with that understanding of the formulas, when you look at this, it's basically your specs spread. In other words, the length of your specification, your upper limit minus the lower. And you compare that to the denominator there, to the process spread. So it's spec spread compared to process spread. And the same for both CP and PP. So let's have another file here. Hopefully you can see this all. Basically, I have my lower spec limit out here in the red on the left side and my upper spec limit on the right side in the red. Basically, anything in between those is considered good product. And when your CP or your PP is 1, that means that your process spread, meaning 3 standard deviations to the left and 3 standard deviations to the right, is exactly the same distance as your spec spread. So you can see this is an example of a CP that is 1, because let's say your lower spec limit minus your upper spec limit, that's 6. The distance between that is 6. Now how big is your process spread? Well, it just happens to be 6 as well. So it's 6 divided by 6, which is 1. Now what happens if my standard deviation is more? The process starts to spread out, right? So now you can see this is obviously not capable, because you have product that's out here in the red, product over here in the red. So something like this, you might have a CP of something like 0.5, because your process spread might be something like 12, and your spec spread is only like 6. 6 divided by 12 is 0.5. So with CP, the lower, if it's less than 1, that's not good. That means that your process, like this blue curve, is putting bad product out there, non-conforming product. But as your standard deviation gets worse, obviously it can get much worse, but as it gets better and as your distribution gets tighter, you get a CP of 1. Let's say it's even tighter than the spec spread. For example, watch the blue distribution here. Let's say your spec spread is 6, but your process spread is only 4. So that's good. 6 divided by 4 is 1.33. Never was good at math. Is 1.5, sorry. So 1.5 CP is good. Basically anything over 1.33 is considered capable. Sometimes people consider 1, being that measure of whether it's good or bad or not, or capable or not capable. But anymore, with the competition and industry, that capability number keeps rising, because customers want better quality, and to do that you need a better capability index. So that's kind of how you read that. A 1 is kind of considered the middle of the road. If you have a CP or PP of 1, then it can be capable, with a little bit of work to the process, but really that's kind of the cutoff point. If it's any less than 1, you probably need to really get back into the process or look at even a different way of doing it. So that's just an example. Again, it's the same as CP and PP. It's just the difference being how standard deviation is estimated, and that's what I'll get into on the example. When you start talking CPK and PPK, what that does is it not only looks at does your distribution fit, but is it centered. So for example, maybe my distribution has a capable, it's very capable of fitting within the spec, but maybe it's over here on the upper spec where I'm producing half of my product as non-conforming. Anytime your average falls on a spec limit, that means your capability, or your CPK and PPK, is 0. And if it's past that, if your average is out of spec, your CPK or PPK will be negative. Okay? So if it's out of spec, your CPK, PPK would be negative. That's your average. If your average is right on the spec, your CPK, PPK would be 0. And if it's within spec, it'll be some positive number. It may not be a big number. It might be like 0.1, or it could be 20. You don't know. It just depends on how tight the spread is and where it's located within that spec location. Okay, so with that, I'll go ahead and get into the example. here to calculate CP based on our data. If you look at the formula, we have the process capability index, upper spec minus lower spec. That's our spec spread. So I took upper spec of 28.75, lower spec of 21.25 to get a difference of 7.5. So that's my spec spread. That's my numerator. Okay. Now, here's the tough part or tricky part. You have to divide it by this 6 standard deviations, this 6S here, 6 standard deviations. Now, the way that you get standard deviation with CP and CPK is using something called R bar divided by D2. And what it does is it looks at the average range. So for example here, you have an average range within your measurements, and that's what R is. Okay, each one of these represents an R, a range. But the challenge then becomes, okay, now you need the average range. So what you have to do is take the average of those ranges up there. Okay, that becomes your R bar. Bar just means average. And if you ever see a double bar or 2 bars on top of each other, that's basically the average of averages. Don't you love statisticians? Okay, this D2, now this is just a constant, okay? Basically what you do is you look up the sample size. It's in an appendix in the back of your books, basically in section 12 on page 12. Okay, and there's a chart there, and it has N, and it goes down the different sample sizes. So for us, our sample size was 3. I was thinking it was 2, but you look over all the way, it's the third last column. If the sample size was 2, it would be 1.128, but in this case our sample size was 3. So let me get that changed. Sample size is 3, which yields a 1.693. Tricky. So that is our D2 in this example, because we have 3 different samples, front, middle, and rear. Okay. So that's why your D2 is 1.693. Okay, now I'm just going to quickly go in and plug that in because I think I messed it up down here. 1.128, that's not that. I'm just changing my D2 constants. Okay, now back to this example. So to get the process spread, you have to take the average divided by D2 and times 6, because it's 6 standard deviations. You can see it here, 6. So 6 times my R bar, which is my range, divided by D2. Okay, so I just did the math, 6.169. So I got the numerator, I got the denominator, I need to divide those two, and you come up with a CP of 1.216. Okay, 1.216. So generally speaking, you want a CP of 1.33 or better. I would say 1.216 isn't bad. I've seen better. It's something that I would say you definitely want to work on it. But that's one way of looking at it. That's referred to as short-term capability, and the reason it's called short-term capability is you're looking at it in a small window. You're looking at the range, the deviation of 3 samples, and that's it, and then 3 samples, and that's it. It sort of is a narrow perspective, if you will, of standard deviation. That's why they call it short-term capability. Now, why do they use it then? If it's only an estimate and it's a narrow perspective, why use it? Well, back in the day, there was no computers. If you ever had to calculate standard deviation by hand, it is not fun at all. So when you're out on the floor, it was easy to just take a number and divide it by the D2 constant versus actually calculating standard deviation. So that's why you have the CP and the CPK, measurements, because it was easy to get calculated out on the floor. All right, but this CP, now this says whether the process is capable of producing good parts. What we do with like CPK is it tells whether you're actually producing good parts. So don't misinterpret this CP number. Okay. Let's go ahead and calculate PP. What this does, instead of looking at it from a short-term perspective, it looks at it in terms of the whole thing. So it's very holistic. When you calculate standard deviation, as you see, the formula is the same thing, only the standard deviation is not an estimate. It's actually standard deviation. You can see the formula here. It looks at all the samples of the data, calculates the standard deviation within a click of a button, so it keeps it simple. Obviously, to get the process spread, you need to take that number times 6, because there's 6 standard deviations in the process. You do the math, 7.5 divided by 6.8, and you get a PP of 1.1. Now normally, because it's a holistic number, you'll consider 1 as the capability cutoff point. Normally your CP is greater than your PP, so this now is pretty typical of what you would see in industry. Let's go ahead and scroll down. So that's what this tells me. Again, similar to the CP, is don't quit working on a process. There's definitely opportunity there. I would say in some industries like medical field, they actually shoot for a CP and a PP of 2. So you can see we'd probably have a long ways to go if that was the case. So a little bit of work to do here yet. Now, CPK and PPK tells us how centered is that process. Remember, when I did the example, I'll just do it for you real quick. What CPK and PPK is looking at is where is it considered. That's the green in the background there, sorry. Let's do this one. Where is that blue distribution within that spec limit? That's what CP and CPK is looking at. Okay, is it out of spec, in spec? Where is it at? So that's what CPK and PPK look at. So for CPK, it's actually a 2-part equation because it's a minimum number of 2 different formulas. Basically what you do is you take your upper spec limit minus your average, and that kind of locates it for you. That tells you, is it within spec or not. Remember I said if you got a CPK of 0, that means you're right on the spec limit. So what that would mean is your upper spec limit is exactly the same as your average, because the location would be 0. And remember I said if it was a negative location, that means you're out of spec. So let's say your upper spec was 28.75. Let's say your average was 29. That would give you a negative location. That's why the CPK number would be a negative number. Okay. R bar D2 to estimate your standard deviation. Now you got to pay attention to the formula here. It's 3 times the standard deviation, because you're only looking at half of it, because you're going from the average to the upper spec. You're looking at half that process. So 3 times the standard deviation in the numerator, or denominator, excuse me. And then you divide these 2 numbers. Location divided by your process upper, 1.155. And then you have to do it for the other side of the spec limit. This time you take your average first, subtract your lower spec limit, and that gives you a location from the lower spec. Okay? And then you divide that, by your estimate of your standard deviation. So R bar divided by D2 times 3. Remember, we're not looking at the whole process spread, we're looking at half of it. So we're going to take it times 3, and that number, take location divided by process lower, you get 1.28. Now CPK is actually the minimum number between those, so that's why I highlighted the 1.155. Okay. PPK, it's the exact same thing, calculated the exact same way, except you're not estimating it. You're not estimating standard deviation. you're actually using the standard deviation. So you can see here I got standard deviation instead of the R bar D2, but I still take it times 3. Times 3. You do that for the upper, you do it for the lower, calculate the number out, and you basically get these two numbers here, 1.048 for the upper side, 1.16 for the lower, and your PPK, PPK is the minimum number between these as well, so it'll be the 1.048. Okay? So if I look at the homework or the discussion forum, what are the assumptions that must be verified when analyzing capability? Does the data meet those assumptions? First of all, you must always ensure that the data fits the normal curve and is statistically within control. And it is. I double checked that before we did this. Number 2, your CP and PP, actually the CP number will be off because I used the wrong D2 number. So shame on me, but now we know that the CP is actually 1.216, so that's incorrect there. But the PPK is still okay. It's 1.1, that's fine. And basically the data is demonstrating that the process is on the edge of being capable. If the process is going to be used, the variation must be decreased to ensure some breathing room. Otherwise, it's likely that it will eventually yield a non-conforming dimension. Okay? And then the third question is the CPK and PPK. What does it tell us? CPK, again, is wrong. It's not 0.77. I used the wrong D2 number. It's actually the 1.15 or 1.16. But still, it would be the same conclusion. Based on this information, the process is performing about as well as can be expected, meaning the process is centered within spec. The variation, though, is definitely concerning because the CPK does not meet the standard minimum of 1.33. The process should be looked at further to reduce variation. Okay, so that'll conclude our session, and hopefully that has cleared up some questions. Thank you.